My name's Jonathan Evans. I'm with Santec USA, and the title of my talk today is Beyond Imaging. Really, we've been extending the usages of OCT technology, which has primarily been used for medical imaging, but we're exploring industrial applications for this technology. So the outline of my talk is, I'll just start with a brief summary about Santec's tunable lasers and imaging, and then the three applications of new applications of our technology: an optical profiler, inline process monitoring, and finish up with Fmcw Lidar. So many of you may know Santec from our tunable lasers. We've been an innovator in tunable lasers. We developed the first continuously tunable diode laser back in 1987, and we're presently on our 7th generation of this type of laser. In 2005, we developed another type of laser, which is specifically for swept source optical coherent tomography. And we have a range of lasers centered at 1 micron, 1.3, with wavelength scans up to 170 nanometers, scan speeds up to 400 kilohertz, coherence length up to 200 nanometers from the latest VCSEL lasers. And as a manufacturer of the laser, we can really customize these sources for different applications. So as I say, we've been doing mainly medical applications. You can think of ophthalmology, dermatology, endoscopy, or cardiovascular imaging. In fact, we do make a FDA-approved ophthalmic instrument. So if you go to your doctor, you might be tested on a Santec system. But since OCT is good for this type of imaging, we're looking to extend it to other applications as well. So just a quick primer on the principle. OCT is really a coherent OFDR, and it has some notable advantages over other optical techniques. It's inherently high sensitivity, wide dynamic range. You can get deeper measurement depths and faster speeds. But the building block of this technology is the swept source. So you can see it scans in wavelength versus time continuously. We send that signal to a interferometer containing a reference arm and a sample arm, whatever we're interested in measuring. These signals are recombined and detected on a balanced photodetector. So what we measure is interferometric signal, but with FFT, we can derive the point spread function, the displacement of which is proportional to the position of the sample. So you can get a high accurate measurement of the displacement of a surface using this technique. So the first application I want to highlight is our new optical profiler, OPS 1000. And we're using these inherent advantages of coherent OFDR to bring to the profiling applications. So again, high sensitivity, single beam geometry, long measurement range, and high speed measurement, and insensitivity to ambient light. So the video is just running through some of those key advantages, which I'll go into more detail. First up, high sensitivity. Well, how does that affect our measurements? So the way you can think of this is, since it's got a high sensitivity, you can detect a small number of photons coming back. So if your sample is glass or blackened, or at a steep surface, meaning that few photons are coming back to your detector, this type of coherent system has a better chance of detecting it. And the example I give here is a drill bit. With the OPS, you can see we can distinctly see the edges, or the highly scattering edges of the drill bit, when compared to perhaps a conventional technique of confocal microscopy, where you start to get a blurring of the actual blade surface, whereas it's very sharp in the OPS 1000 image. Features 2 and 3, the single beam geometry and long beam measurement range kind of go hand in hand. If you traditional metrology systems may have a light source and detector separated in space. So you get into this kind of instance where surfaces will be occluded from the light being able to reach the detector. Whereas if you're using a common path for both your analyze and detect beams, you can see deeper into the object. And the fact is we can set up the coherence length of our system. So we can go up to 1 meter in imaging range in depth, which is far larger than the other systems out there. High speed I mentioned, well, our lasers can scan up to 400 kilohertz, so 400,000 points per second can be measured. So how does that come into play? Well, again, going back to the drill bit, the OPS acquired that image in 5 seconds, whereas the conventional confocal microscope took 1200 seconds. So you're talking about, for the same resolution, the same area covered, seconds in terms of the image acquisition over minutes. And the final feature is the insensitivity to ambient light. So it's a coherent technique. So stray light, sunlight, other sources of light that are not incoherent with our measurement signal will not be detected and don't interfere with the measurement. So taking a fairly extreme example, here's a welding system where it's in the presence of a multi-kilowatt laser, but we can still get this nice profile of the keyhole shape, even under those conditions. So OPS 1000 launched this year. It's got 3 standard specifications, really differentiated by resolution and scan range. So if you would like to learn more, please join us in the breakout room after the meeting. The second application is inline process monitoring, and I'll talk about welding and silicon wafer polishing. So in the center here is a typical setup for a high-power laser welding system. You've got a multi-kilowatt beam coming down onto the metal where the welding is taking place. At the focus of the high-profile beam, there's this ablated region called the keyhole, and to assess the quality of the weld, it's important to have a real-time monitoring of that, of the geometry of the keyhole. So here you can see the OCT, or the image of the keyhole using our system, and the algorithm pulling out the actual surface of the keyhole. We can see that in process here. I've got the video is not playing, okay. So anyhow, so what we did here was look at the measurement of results during the welding process, which is the yellow line. And then we took the weld and cut it in half and compared the depth of the weld after the fact to the measured. And you can see the very good agreement between the in-process measurement of the weld depth compared to the actual weld depth that was assessed post-process. So a nice use of this technology, inline process monitoring. So the second inline processing I wanted to discuss was wafer polishing. So this is silicon wafer polishing, and our probe beam comes down from the top. You've got your wafers in the polishing system. They go around and they're gradually ground down. So the key takeaway from here is that we can get tremendous high resolution on the measurement of the thickness. So this plot is the thickness versus time, and you can see it decreasing as the wafer gets thinner. And the actual resolution we're getting on this measurement is 10 nanometers. So we're really into that sub-micron resolution on this measurement. And you can do that across the whole width of this 300 millimeter silicon wafer. So again, a nice use of this technology, which we first used for medical imaging into industrial applications. I'll finish up with Fmcw Lidar. It's quite a hot topic right now, and especially in certain applications, 3D mapping, security, robotics, but maybe most hot right now is mobility with sorts of autonomous cars. And we have a simple objective at Santec, was to simplify solid state Fmcw Lidar. And you can go to this publication below. My colleagues published in Optical Express more details about this work. But at the top, just a brief summary of the process in Fmcw Lidar. Actually, this is just the same as a customized OFDR, coherent OFDR system. So we're quite familiar with this technology. So the advantages of the long detection range, eye safety, immunity to ambient light, and you can also get velocity measurements out of an Fmcw Lidar system. There are challenges. Well, sophisticated technology is required. Well, it's the same as the technology that I described above for our other imaging systems. We've got a specialized tunable lasers. The Santec Tunable VCSEL is really a nice source for this measurement. And the optical signal system is complex. So what I'll present here is just a quick a summary of how we're simplifying beam steering in this application. So I mentioned our VCSEL laser. It's called the Hsl1 Laser, and this actually scans 88 nanometers in range. And this is far more range than you need for the resolution required for a good LiDAR system. So it gives us an opportunity to use this together with a dispersive element to do beam steering. So here's the a schematic of what we're doing is we have a dispersive element upon which our laser beam is focused. And then because it's dispersing the beam via wavelength, we can segment it into different channels for ranging. So here we've segmented it into 30 segments, and then with the interference signal, we do the same thing. We do that segmentation. So in practice, here you can see the beam steered across the target, and no moving parts here, right? All we're doing is using a diffraction grating to scan the wavelengths across the target. And then as we get the interference pattern back, we segment it into those 30 channels, and we can build up the point spread function and get the LiDAR image of that target. So that's pretty neat new application of our OFDR technology. Good. So I hope that gave you a quick summary of what we're doing at Santec right now. I'll be going into the breakout room after this session, where I'm joined with Nikita from our New Jersey office, and we'll be happy to take any questions you might have in the breakout room. Thank you very much.